A review of acid-base equilibrium for Chapter 14. The Bronsted-Lowry acid-base theory says that an acid is a compound that donates protons, H+, and a base is a compound that accepts protons, H+. The conjugate acid-base pairs. A base will accept a proton and become a conjugate acid, and an acid will donate protons, H+, and become the conjugate base. Conjugate acid-base pair in the reaction. Two compounds which differ only by the hydrogen ion. Two compounds must be on the opposite side of the arrow. The amphoteric substances. Substances that can act as acids or bases. This, for instance, can be water, where it produces hydroxide and H3O+. It could also be hydrogen carbonate, which can produce carbonate or H2CO3. The monoprotic acids contain only one ionizable proton. Diprotic acids contain two ionizable protons, and triprotic acids have three ionizable protons. Water is amphoteric. Autoionization, a reaction of water molecules transferring hydrogen protons to yield hydronium, H3O+, and hydroxide ions, OH-. The ion product constant for water, Kw, is the equilibrium constant for the autoionization of water. Its value is 1.0 times 10 to the negative 14. Here we can see the autoionization of water, where the water molecule breaks down into hydroxide and hydronium ions. And Kw is the concentration of the hydronium and the concentration of the hydroxide ions. Ion product constant for water, the equilibrium constants for the autoionization of water. For acids, bases, or pure water, 25 degrees Celsius, Kw, as stated before, is the concentration of hydronium times the concentration of hydroxide ions, and it yields 1 times 10 to the negative 14. pH is defined as the minus log of the hydronium ions. And the reverse of that is the concentration of a hydronium ion is equal to 10 to the power of minus pH. And pOH is defined as minus log of the hydroxide ions, and pOH is equal to 10 to the power of minus pOH. pKw is defined as pKw is equal to minus log of Kw, and Kw is equal to 10 times to the power of minus pK. pOH plus pOH is equal to pKw, or 1 times 10 to the negative 14, and pH plus pOH is equal to 14. As pH increases, hydronium concentrations decrease and hydroxide concentrations increase. pOH decreases. As pH decreases, hydronium concentration increases and hydroxide concentration decreases. pOH increases. Here we see that conversions between the hydronium concentration, pH, hydroxide concentrations, and pOH. We can see the transfer that happens with multiplication for going from one to the other. When going from pH to hydronium, or from pOH to hydroxide concentration, we use log or 10 base. When going from pH to pOH, we use subtraction from 14, and from going hydronium concentration to hydroxide concentration, we use the formula that hydroxide times hydronium is equal to 1 times 10 to the negative 14. For pH, in a neutral compound, the hydronium and hydroxide concentrations are equal, meaning that pH is 7. In an acidic compound, the H3O plus or hydronium concentration is greater than hydroxide concentration. This is because the acid gives hydrogen ions to the and creates more hydronium, and the pH is less than 7. For basic solutions, the hydronium concentration is less than the hydroxide concentration, and pH is greater than 7. The normal range of pH is from 0 to 14, and pH of 0 is that the hydronium concentration is equal to 1 molarity, and pH 14 is that the hydroxide concentration is equal to 1 molarity. Here are some of the strong acids and strong bases: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid. Some weak acids include formic acid, acetic acid, and hydrofluoric acid. Strong bases include lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. The weak bases include ammonia and N-containing compounds. pH of strong acid solutions. When determining the pH of strong acid solutions, we must understand that strong acids react completely when dissolved in water to yield hydronium ions. One equilibrium lies far to the right, which means hydronium ion is formed. So we know that because all of the initial acid concentration reacts to form hydronium ion, we can say that the concentration of hydronium ions is roughly equal to the initial acid concentration. We can use the concentration of hydronium ions in the pH minus log the concentration of hydronium ions to figure out the pH of the solution. For the pH of strong bases, again, we must understand that strong bases completely dissolve in solution to yield hydronium ions. And for group 1 metals, 1 mole of substance is equal to 1 mole of hydroxide ions. So, hydroxide ions, the concentration of hydroxide ions is equal to the concentration of bases initially. For group 2 metals, 1 mole of base produces 2 moles of hydroxide. And we can see this previously here as well. The calcium, strontium, and barium, they produce hydroxide with a 2 under them. And therefore, here they produce 2 moles. 2 moles of the initial base concentration produces 2 moles of the hydroxide. pH of weak acids. Weak acids partially ionize in solution to yield hydronium ions. For instance, so the value of a hydronium ions is smaller than the initial acid concentration. Therefore, the acid ionization constant, Ka, the equilibrium constant for the ionized direction of weak acids, is determined, and pKa is equal to minus log Ka, and Ka is equal to 10 to the power of minus pKa. When the Ka value is larger, the pKa value is smaller. We can see it here in the equation above. And the pH is lower. When Ka value is smaller, the pKa value is larger, and pH is higher, meaning less acidic. For weak bases, only a small fraction of weak bases accept protons from water. So for weak bases, hydroxide ions is smaller than the initial base concentration. Again, as with acids, the base ionization constant Kb is equal to the equilibrium constant for the ionized reaction of the weak base. And here we can see the same thing. As Ka gets larger, pKa gets smaller and pH gets higher. As Ka gets smaller, pKa gets larger and pH gets lower. Common weak bases are a molecule with nitrogen ion with a lone pair that accepts protons H+ from water to make a base. They also include carbonate ions and bicarbonate ions. Calculating Ka or Kb. If given the equilibrium concentrations, all equilibrium concentrations, you can use Ka or Kb expressions directly. But if given the initial concentration and pH, you have to use ice tables and calculate the concentration of hydronium ions and use pH minus log of hydronium times the minus log of the hydronium concentration is equal to 10 to the power of minus pH. Calculating the pH and equilibrium constant for the initial acid or base concentration and Kb values. You have to write the ionization reaction of Ka or Kb, prepare the ice table to find the concentration at equilibriums, and for the pH, you have to know that for weak acids, pH is equal to minus log of hydronium ions, and pOH is equal to minus log of hydroxide ions. pH is equal to 14 minus the pOH concentration calculated above. A shorter method for doing this can be that if you know the initial concentration of the acid and the Ka value, you can take the square root of it instead of performing the ice table and get the hydronium concentration. Then you can take the minus log of this concentration to find the pH. Similarly with bases, the same thing can be done, but you must subtract 14 from you must subtract this value from 14 to get the pH. Finding the pH of mixtures and acids. So for a strong and a weak acid, the strong acid contributes to the total concentration of hydronium. For two weak acids, the acid with the higher Ka value, or the stronger acid, contributes to the total hydronium ions. And here we see that pH, once we have the hydronium ion concentration, we must take the negative log of it to find the pH. Percent ionization. For weak acids, it's the concentration of ionized acid and divided by the initial concentration of acid times 100, leading to the percent ionization. This may look like the concentration of hydronium ions divided by the initial acid concentration times 100%. Weak base. For the concentration of ionized base divided by the initial concentration of base times 100 is equal to the percent ionization, and it looks like hydroxide concentrations divided by the B value times 100. And the higher the percent ionization, higher the acid or base strength. Binary acids. They are hydrogen attached to a metal. The general formula is hydrogen with N at the bottom and A. And the strength of an acid measures the ability to donate the hydrogen ions. So they are strongly affected by two factors. The strength of hydrogen and the A bonds, which happens as electronegativity increases. We see that it becomes easier to separate the binary acids, and the strength meaning the ability to donate hydrogen ions increases. This is also affected by the polarity of HA bonds. So as the size of molecules increases, a dipole can form more easily and bonds become weaker. So the binary acid strength increases. Oxyacids are a hydrogen atom bonded to an oxygen atom that is attached to a nonmetal. This can look like HNY, the metal, and O to the M. Electronegativity of a metal. If it is the same number of oxygen attached, then as electronegativity increases, the HO polarity increases and the atoms become easier to split, and the OA strength or the increases. As the number of oxygen atoms attached to Y increases, the polarity increases and OA strength increases. Therefore, we can see as we approach the top right corner, the OA strength increases. Here we can see that as we approach the bottom right corner, the OA strength increases. For any conjugate acid-base pair, K of A times K of B is equal to minus K of W is equal to K of W and is equal to 1 times 10 to the power of negative 14. You can use Ka or Kb to calculate the other for the conjugate. For instance, if an acid is used, then you can calculate the Kb for the conjugate base. And it's good to remember that the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base. This illustrates the pattern below. As the Ka value increases, the Kb value decreases, and as the Kb value increases, the Ka value decreases. This is also true for bases. Acid-base properties of salts. A salt is something with a cation and an anion. So a cation can potentially serve as an acid and donate hydrogen ions to water. An anion can potentially serve as a base and accept hydrogen ions from water. Cations that form strong bases cannot donate hydrogen ions to water and are pH neutral. Weak bases can donate hydrogen ions to water. They form H3O plus in water and make the water more acidic. Therefore, it is pH active. Anions, meaning strong acids, cannot take H plus to water and cannot take H plus from water and are pH neutral. Weak acids can take H plus from water and they produce hydroxide in water and lead to the water becoming more basic. Therefore, it is pH active. If both weak acids and weak bases are present, then it is either pH neutral, or if the Ka value is greater than the Kb value, then the solution is acidic, or if the Kb value is greater than the Ka value, then the solution is basic. To calculate the pH of a salt, identify the species which can influence the pH of a solution. Determine the Ka for the cation or Kb for the anion for the pH active species. And we can do this because we know that Ka times Kb is equal to 1 times 10 to the negative 14, and then write the ionization reaction in Ka or Kb expression. You can perform the ICE table or the short method. I've listed the short method below,